This is our quick review of differential equations. Make sure that you pause and go back and listen again if there's any part that you miss along the way or have forgotten. So you can read along on your handout. So we started out with differential equations at the beginning of the year that we knew the antiderivatives. So that's what we're practicing here in these first three examples. We know that negative cosecant squared is the derivative of cotangent, and then we learned that there's a whole family of antiderivatives. So now we can think of this as integration and adding a constant. The antiderivatives differ by a constant. And in our second problem, we know this first term is the derivative of cosecant x, and the second term is the derivative of 7x, and then we would add our constant. And our third problem, we would reverse the power rule. We raise the exponent by 1 and divide by it. And this x to the negative 1 is 1 over x. You could try the power rule, but if you added 1, you'd get to 0 power, so you would know that's a mistake. So this is 1 over x. It is the derivative of natural log of x. And then we add our constant. All right, and then we talked about in second semester, what if we had a differential equation and we didn't know the antiderivative? Well, we learned that slope fields are a visual way to get a picture of all of the solution curves. So some shortcuts, we remember that if the slopes in each row, a row is horizontal. If all of the slopes in a row are consistent, then we know that it depends only on the y variable, and some textbooks use the term autonomous to describe that type of differential equation. If the slopes in each column, columns are vertical, if the columns are consistent, then we know the differential equation has only the x variable in it. If a row contains all horizontal tangents, that means the derivative was equal to 0. That is called a constant solution. And it's very important and helpful to look for constant solutions first. And then we know that the other types of solution graphs reach equilibrium at that point. So they reach an equilibrium when they reach that horizontal tangents. All right, so how do you find constant solutions? Well, when is the derivative equal to 0? So this derivative is equal to 0 when the numerator is equal to 0. And of course, that numerator is factorable. The denominator is prime, but the numerator is y plus 3, y minus 2. So there are two lines when y is equal to negative 3 and when y is equal to positive 2. So on the slope field, there would be two constant solutions. They would be rows of horizontal tangent lines. Is y equals 4 a constant solution of this equation? Does it make the derivative equal to 0? Yes, it does. So does a solution curve reach equilibrium? I assume this is referring to the previous question. So when it reaches that row of horizontal tangents, so remember you might have a solution curve that's rising, but then on your slope field, once it hits those horizontal tangents, then it's going to level off and reach an equilibrium state. All right, so some quick reminders here. What can we conclude? I just want to get this visible for you. What can we conclude about the differential equation? Well, the first thing I notice is that these horizontal rows are all consistent. So we know that the differential equation depends only on y variables. So there are no x's in our differential equation. But a second glance here, do you see that all of the slopes are exactly equal here? So I'm going to tell you that this was because I took this slope field from this equation where dy dx is always equal to 1. So those slopes are always meant to be equal to 1. So now that I've given you that differential equation, you can tell that they were all positive, but you'd have to know the units to know that that's equal to 1. Now the next question says, now could we find out a general solution? So could we work backwards and say where this came from? So isn't 1 the derivative of x? So we don't even need to separate our variables here. So there's a general solution for that slope field. And then another slope field, what do we notice here? Well, I hope pretty quickly you would notice that if you read vertically, that each vertical column is consistent. So this differential equation depends only on x. And then you might say, well, look at what's happening here. When the x variable is negative, the slopes appear to be positives, and when the x variables or when the x values are positive, the slopes happen to be negative. So you should also notice symmetry and how the relationships happen between the x values and the slopes. So again, you might not recognize this immediately, but I know that this slope field is from the equation dy dx is equal to the opposite of x. So at -2, the slopes are +2. And at +2, the slopes here are -2. So again, the next question, once I give you this equation, and you might have guessed something similar to that, but you wouldn't have known unless I told you that that was the differential equation. But now that we see that differential equation, can we reverse this one? Do you know that -x is already the derivative? So we don't even have to separate the variables because there are no x's and y's to separate. So if you know the antiderivative, and then here, once I use the power rule, don't forget to add a constant. And now let's take a look here. If I asked you to graph one of the solutions, say the solution that goes through the point 0,2, do you see what happens when you follow these tangent lines? So does it look like this solution could be a parabolic solution? So the slope field kind of matches. I could do the same thing in the previous one, by the way. So if I graphed one of these, it would give me a line with a slope of 1 and same line with a slope of 1 but different y-intercepts for the solution curves. All right, the next slope field, what do we notice? And again, I see horizontally that these are consistent. So the first thing that's always apparent is that it depends only on one variable. That's not always going to be the case, of course. So the differential equation depends only on y. And we might do the same thing here to look about the comparison of the signs. So do you notice that when the y values are positive, our slopes are positive, and they're getting larger? We can see the slopes are getting steeper. And down below, when the y values are negative, we have only negative slopes. So again, you might come up with some ideas of what this differential equation could be. I chose this slope field for this problem, and I'm going to tell you that the slopes are exactly equal to the y coordinate. So now we have a different type of differential equation, and we would have to separate the variables here. So I would, to solve question 14, I would move the y to the side with the dy, and I would keep 1 on this side with the dx. You don't have to write a 1, by the way, but I think it's a helpful reminder for students. And then when we integrate, remember this is the natural log of absolute value of y. And then to solve for our general solution, we have to exponentiate both sides. So we do e to this value and e to this binomial. So we'll come up with y and the absolute value of y. And here, remember what we did? We split this up. When do you add exponents? That would be when you're multiplying. So this value, and I'm going to call this C1 because in my next step now, I'm going to take this value, e to a constant, is a constant. So we have the absolute value of y is equal to a constant e to the x, and the absolute value could depend on whether that constant is a positive or a negative value. And if I asked you to graph this equation and I gave you a specific value of c, so one particular solution might be negative 2 e to the x. So do you see then that we have a curve? When we have negative exponents, we have our curve. Sorry, that didn't hit very well. I should erase that and get a little bit higher. So do you see how these curves can be negative exponentials? And another example, if we had a positive constant, like 1e to the x, here's our graph of 1e to the x. So they have positive slopes and negative slopes depending on the value of c for our basic exponential function. All right, what kind of questions should you be preparing for on your AP exam? You should pause the video and take a look at these types of problems and these suggestions. I think it's a very helpful reminder. After you've studied those two lists for your review purposes, then we'll continue on with question 16. And we're just going to do some quick comparisons of if you had to match a differential equation to its slope field. So two that look very similar, and these might be given to you in multiple choice form, but we know that the sign of 0 is 0. So let's think about that to compare these two. So here they're written again. So what would you expect the slope to, when would it be 0? So if this parenthesis, so if y is equal to the opposite of x, then dy dx would give us 0 because we would have the sign of 0. And in our second equation, when would this be equal to 0? When y is equal to positive x, then dy dx would be equal to 0. So how does that help us? Well, look at, this is our 45-degree line. So if you look as you proceed, looking at the 45-degree line, and it's not always, our slope fields aren't always printed so that you can see all of these horizontal tangents, but and it all depends on the resolution and the size, but can you see some horizontal tangents there on the line y equals x? So this second that I'm doing in blue would match slope field B, and the one that I wrote in red here, when y is equal to negative x, let's see if you can see some horizontal tangents here. And again, it all depends on the resolution and scale of the slope field, but I think we see what would be horizontal tangents there in our line y equals negative x. So slope field A would match this differential equation. All right, similarly, what if we had to match sine of x cubed versus sine of y cubed? Well, let's do the same idea here. So when x cubed is equal to 0, that of course is equivalent to saying x is equal to 0, then dy dx, the slopes will be equal to 0, and compare that to using the sine of y cubed. So, this one we would have, if y cubed is equal to 0 or y equals 0, then we would have horizontal tangents. So here we simply need to look for the horizontal tangents on the x-axis or on the y-axis. So when x is equal to 0, this is our y-axis. So notice that here it looks like we have our horizontal tangents. So I think this one matches slope field B. And on our y equals 0 line, that's our x-axis. There's our horizontal tangents. So this one matches our slope field A. In question 18, we have the product of these values. So the point here is that by comparison, we can use the values that produce positives, negatives, and zeros. So here, if x or y is equal to 0, then we would have cosine of 0 for our slope, and the cosine of 0 is equal to 1. So dy dx would be equal to a slope of 1 on either of the two axes. So notice here on this vertical axis we have horizontal tangents, but on this axis we have slopes of 1, and on this axis we have slopes of 1. So we've already identified that that should be A. Now let's compare it to the other one, the sine of the product xy. So if x equals 0 or y equals 0, then we would have the sine of 0, which is equal to 0. And dy dx would give us horizontal tangent lines. So looking at the axes, can you see that in this axis we don't actually see the horizontal tangents, but right above it they are positive, and right below it they are negative. So it must have hit 0, which isn't very easy to see on top of that slope field. All right, so the slope fields gave us a visual picture. How did we solve differential equations algebraically? Well, if it was possible, we solved them by separation of variables. Not always possible, but if you have products and quotients that you could separate. So we multiply y to the opposite side to keep it with the dy, and we move the differential dx to the right-hand side, and then remember that we integrate to find our antiderivatives. So we would have 1/2 of y squared and 1/2 of x squared. And the question, the first time we did this, we said, shouldn't we add a constant on both sides? And yes, we should, but your very next step, you would combine them on one side. So we saved a step and just put the constant on one side. And then we want to solve to get a function of y, or y equals a function of x, rather. So let's double everything here. And that's where subscripts might come in handy here. We can now say that this is still a constant, but we've changed it, we've doubled it. And then we want to solve for y, and notice that we still don't have one function. We have two branches when we do the positive or negative root. So this general solution is either going to be the positive branch or it's going to be the negative branch, so that it is a function and passes the vertical line test. So this is our general solutions. And then in part B, we're asked to find a particular solution when we have an initial value. So now we need to find C. So we could either take this step, or we could choose from the positive negative step. And this is where we knew that y is less than 0 for this solution point. So that's how we know that we want to keep y negative for the entire solution. So it's going to be this branch that we're interested in. And we could put -4 in for y and 3 in for x, and square both sides. And we have C is equal to 7. So our particular solution, and I ran out of space a little bit here, is this opposite of the square root of x squared plus 7. So that is our specific solution. So remember that we can't keep both the positive and the negative branches. You would choose one branch, and you choose it because if this solution point has a negative y, that tells us that we're keeping the branch where the y coordinates are negative. All right. So remember that the solution is going to have the largest possible domain, and you have to avoid discontinuities. So we can't keep two separate branches, and we can't jump across vertical tangent lines on a slope field. So sometimes we need to restrict the domain. And that's something that we didn't spend a lot of time on the first time that we were doing this unit. So let's be a little more precise here. When we look at this differential equation, do you notice right away that there is a domain restriction? X cannot be equal to 0. So we're going to have to choose our domain for our solution curve. So as a hint here, this is not part of what you have to write, but remember that your solution will stay on only one side of x equals 0. So our x's will all be positive or they'll all be negative. And again, how are you going to choose? Your initial value is going to give you a pretty good idea. So it's not a difficult question here. All right, now let's go back and separate our variables here. So there's not much to separate. We're going to move the dx to the side here with the 1 over x. And then we're going to integrate both sides. So again, you can put a 1 here in front of the dy if that's helpful. But our antiderivative, this is the derivative of y. And this is the derivative of natural log of absolute value of x. And we add our constant. And I chose this because it's an excellent chance to review for you that when you graph the natural log of x, you only could do positive domains. So the natural log of x we think of as just this branch of the curve. So y equals natural log of x, we would keep only positive x's. But as soon as we do absolute value, then that doubles. Now we can have this branch on this side as well. So now you can see why we have to choose. So this is not part of our particular problem right now, but to recall that when you graph y equals the natural log of x, it's a double branched curve, but there's still that vertical asymptote. There's this forbidden value. So x cannot be equal to 0 is an asymptote of those two branches. So we're going to choose between them. All right, so now let's return to our problem and let's use our initial value. We know that when we put -1 into our function, we get 2 as our dependent variable. So we can find out what our constant value is. So the natural log of 1 would be 0. So our constant is equal to 2, since that value is 0. So now we have our graph y is equal to the natural log of the absolute value of x plus 2, but that would still have 2 branches to it. So notice that here, this x coordinate, this solution point, the solution point is on the negative side of x equals 0. So what do we do here? We tack on a domain. So this domain, and you can use interval notation or you could use inequality notation, but we're going to go from -infinity to 0. So this is how you show a domain restriction. And that has come up occasionally on the AP exam. More often it has come up in multiple choice questions, and then students wonder why there's this additional information. So next time you see it, you'll know that that simply means that we're keeping only the negative branch. So this curve is slid up 2 units, so it would look like 2 branches, but we can't keep a discontinuity, so what we're saying here is we're keeping only this part as our solution. So when you solve a differential equation, you're looking for the largest domain for a continuous function as your solution. All right, so one more example where we might have some considerations here, and I'm going to rewrite this. You might miss that -2 is the exponent, so I'm going to rewrite it, y to the negative 2, I'm going to put it down here. So you'll notice that y cannot be equal to 0 this time. So we know that our solution curve, so just as a hint here, and this won't have too big an implication on your algebra, but think about your slope field. The solution curve on the slope field would either be above, so the solution curve will be all above or all below the line y equals 0. So we can't cross over a discontinuity. All right, and we might also end up with a restriction on our x values, so a domain restriction. All right, so let's see, and notice this is an initial value problem, so we'll be able to solve for c. So this problem's already been done for you, but let's repeat it here. So if I separate the variables, so do you want to keep the 3 with the y, or do you want to keep the 3 with the x? That's really going to be your choice. Since it's in the denominator, I'm going to move it with the y. And then when we integrate, notice that this 3 worked nicely with the y squared, so it facilitates our power rule. And on this side, the antiderivative plus a constant. And then when we solve for y, when we take the cube root, we would get the cube root of x plus our constant. And then we've got an initial value, so we know the point 1, 1 is given as a solution point up here. So we can use that to find our value of c. So we cube both sides, and c turns out to be 0. So if you go back and read the solution here, it says that y is equal to the cube root of x, and they have it written in function notation y of x. Those are, of course, the same thing. All right, and here's the thing that we might not notice about this. Notice that this function has no derivative at 0. What are we saying there? Let's look at the derivative of this. If we did y prime, do you see that we would get 1/3 of x to the negative 2/3? Or if we write it as a fraction, it goes to the denominator. So there is no derivative. There is no derivative at x equals 0. So why would that be important? Well, because we would again have a discontinuity. So we want to keep only one side or the other. So we have to keep either. So we have to keep either x's that are positive or x's that are negative, but we can't cross over our discontinuity. So for this problem, we were almost there. We like this as our solution curve, but now we have to add a domain restriction. Should we keep only positive x's or only negative x's? And again, the answer is, where is our solution point? 1, 1 was our solution point, so we want to keep only positive values of x. So again, it's not going to happen very often that you're going to have to remember that much detail, but in a multiple choice question, if you see a domain, you'll know that that's the reason why. All right, now there's some problems for you to try for more practice, and I will do those in a separate video, but would you please practice those problems on your own first, and then you can listen to the video.